Okay, let's get started, everyone. Hello again. Thanks for joining. My name is Ashwin, and today we'll discuss previous year's week three questions. Let me just share my screen. Okay. Can someone confirm if they're able to see my screen?
Yes, sir.
Okay, great. Okay, so good evening, everyone. Today we'll be discussing week three questions from the previous year assignment of drug delivery principles in engineering. Uh, Yeah, so with that, let's jump into the first question, which is what is not correct about reservoir systems with orifice type of implants? Two options are correct here. They can greatly increase circulation of the drug in the body. The device can be excreted in urine and sweat. Drug release generally follows first order kinetics. Examples Procardia XL tablets. The drug sits way out of the orifice. The drug can be released by swelling control mechanism. Any idea? They're asking what is not correct about the reservoir systems with orifice. So can they greatly increase circulation in of the drug in the body? Can they be excreted in urine and sweat? Can drug release follow first order kinetics? Is one of the examples of reservoir systems and with orifice procardia XL tablets? And does the drug find its way out of the orifice, and can the drug be released by swelling control mechanism? Let's take a look at the example that was given in the class, which is reservoirs with orifice. So in this case, these are Procardia XL tablets, which are reservoirs with orifice. So this is a reservoir. The drug cannot penetrate this reservoir and come out of the tablet, but there is a small hole here, if you can see, which is the orifice. So the drug can freely come out of the orifice. Yeah, so that's a reservoir with orifice system. So obviously this is true. Uh, so this is not the correct answer. So we'll go through them one by one once again. Can they greatly increase the circulation of the drug in the body? Yes, right. So just because of the fact that these tablets contain a very large amount of drug and they slowly release the drug out of this orifice, they will prolong the amount of time the drug can circulate in the body. Can these devices be excreted in urine and sweat? Uh, can this tablet be excreted in sweat or urine? It would be very painful to do so, right? So these are not small tablets.
So this type of reservoir system is excreted to fecus.
Yeah, correct. So they're not excreted through sweat and urine, but
Yeah,
instead through feces.
yeah.
Uh, yeah, yeah. So essentially, the drug cannot be excreted through urine and sweat, and it's not necessarily true that the drug release follows first order kinetics, right? Because the main parameter that's governing drug release here is the orifice, the size of the orifice, and the size of the drug itself. So it need not necessarily follow first order kinetics. Okay, moving on. So there's an assertion here, which is when a controlled release formulation is placed in a biological medium, it immediately releases some quantity of drug known as bolus. Reason is this burst effect is attributed to the time history of the device, with older formulations allowing diffusion of some quantity of the drug to the surface. Now they're asking us if both of these assertion and reason are true, both are false, or the assertion is false but the reason is true, but or vice versa, wherein the assertion is true but the reason is false. Any idea? What are they talking about here? So the assertion is when a controlled release formulation is placed in a biological medium, it immediately releases some quantity of drug as a bolus. Is that true? Does that happen in case of a controlled release formulation? So as soon as you place this controlled release formulation in whatever it is, serum, water, whatever it is, immediately some
Sir,
quantity, yeah.
sir, immediately drug will release as a bolus system in sustained release formulation, sir. I think so.
Okay, so controlled release and sustained release are one and the same.
Okay, sir.
I think maybe.
Yeah, okay. Yeah, so there is some amount of,
అయితే मेरी milk పెళ్ళి.
so there is some quantity of drug that is immediately released as a bolus. And the reason they're giving is this burst effect is because of the time history of the device. With older formulations allowing diffusion of some quantity of drug to the surface. So uh, essentially what they're saying is, so let's say this is the controlled release formulation and there is some drug here, and because the device has been kept for quite some time, so old device, so some of this drug is starting to diffuse out and reach the outer membrane, right? So there will be a lot of drug in the outer membrane, and depending on how old it is, this will increase. And when you place this in water or serum or whatever, what happens? So all of this drug will immediately come out. Whereas if you take a new device and do the same thing, what would happen? It will take some time to for the drug to come out. So if you look at the concentrations of the drug, if it's a very old device, there'll be this burst and steady release like this. But if it's a very new device, there'll be this lag and steady release like this, right? So yeah, so we basically this slide talks about the reservoir systems lag and burst effect. So if it's an older device, there is a lot of drug that's immediately released because just because of the fact that it has been old and the drug has been allowed to diffuse out to the outer membrane before the delivery is sort of sustained. And if it's a very new device, then it will take some time for the drug to reach the boundary of the device, right? So that's why you see this lag response. So in this case, yeah, they're correct. So both the assertion and the reason are true, right? Yeah. Any questions? Okay. Yeah, so the next question is avidin conjugated to a polymeric biotin is a type of which type of hydrogel is it? Is it a physical hydrogel, a complex coacervative, coacervate, a chemical hydrogel, ionotropic hydrogel, photolinked hydrogel, or an enzyme linked hydrogel? Any idea? So let's go through what these hydrogels are. So a physical hydrogel is a polymer network that's held together by neutral or ionic bonds, whereas chemical hydrogel is covalently cross-linked hydrogels. And inotropic ones are polymers that form hydrated gel matrices, especially in the presence of metal cations. And complex coacervate is basically liquid droplets that are formed by liquid-liquid phase separation mixtures. So definitely not complex coacervate, right? Because avidin and biotin is a protein, so it's not liquid. So definitely not this. Uh, Definitely not inotropic as well because there is no metal cation that's involved. And what are photolinked hydrogels? Photolinked hydrogels are basically hydrogels that get activated and start cross-linking when particular wavelength of light is shined upon them, shown upon them, right? So in this case, we are not using any photo activation, so they are not photolinked hydrogels as well. And is it an enzyme-linked hydrogel? Not really. There are proteins involved, but we do not use another enzyme to form the hydrogel cross-linkage here. It's just avidin that's forming a bond with biotin. Now, it is either a chemical hydrogel or a physical hydrogel. In this particular case, avidin that forms a bond with biotin, it forms an ionic bond. So it's a physical hydrogel. It's not a covalent bond. So yeah, it's an example of physical hydrogel. Okay. Uh, moving on. So porosity in non-erodible matrix systems can be measured by which technique? AFM, DLS, osmometry, surface plasmon resonance, liquid leaching experiments, electron microscopy, followed by image analysis. How do you measure porosity of a non-erodible matrix system? AFM is atomic force microscopy and DLS is direct light scattering. So, do you use atomic force microscopy to measure the pore size? Direct light scattering, osmometry, surface plasmon resonance, liquid leaching experiments, or electron microscopy followed by image analysis? Any idea?
Sir, last two options.
Last two options. Yeah, so liquid leaching experiments and electron microscopy followed by image analysis, right? So, uh, do you guys know what AFM is used for? Atomic force microscopy. Do you know what it's used
To
for?
understand the surface,
Yeah, yeah, topography
yeah, topography, yeah.
of the material. And DLS, direct light scattering.
Sir, to measure the size of the particles.
Good, yeah. So DLS is used to measure the size of the particle, and osmometry.
Sir, it's used for checking the blood sugar levels.
Yeah, so salt or sugar levels in any liquid medium, right? So that's where osmometry is used for. And surface plasmon resonance. Maybe you haven't covered this in the class, but SPR is also used to study surface level changes, especially when it comes to adsorption. So it's a very powerful technique to study adsorption of proteins, DNA, RNA onto biomaterials. So yeah, so that's what those four are used for, but liquid leaching experiments and electron microscopy. So typical electron microscopy image looks like this. So from this, you know what a pixel's length is, or you know standardized distance measurement. So you can calculate the uh, size of the particles or the average size of the particles from this using image analysis techniques. And liquid leaching experiment is wherein you have this whatever matrix you have. So you put that in and you let liquid leach through it, and you measure the amount of liquid that so you flow liquid through it, you stop the liquid, and you see how much of the liquid is leaching out. So that you know what the pore size is. You can back calculate pore size from that. Okay. Yeah, liquid leaching experiments and electron microscopy followed by image analysis. Okay. So which of the following two statements are false for bulk hydrogels? Hydrogels are three-dimensional hydrophilic polymer networks capable of swelling by absorbing large amounts of fluid. They have predictable or known swelling rates. They are insoluble due to physical or chemical crosslinks, which provides the network structure and physical integrity. They're soluble in water. They have low burst effects. They're used in contact lenses, and they're suitable for all delivery routes. So, which of the following statements is false? Any idea? Okay, let's go through the options one by one. So, hydrogels are three-dimensional hydrophilic polymer networks capable of swelling by absorbing large amounts of fluid. Is this true? So, they are three-dimensional structures, right? So, any polymer that you make is a three-dimensional structure. You cannot make a two-dimensional polymer. So yeah, there are three-dimensional structures. Are they hydrophilic? Are they hydrogels? Are they hydrophilic or hydrophobic?
Hydrophilic.
Right. So they need to absorb a lot. So by definition, hydrogels are as polymers that absorb a large amount of water, right? So they cannot be hydrophobic. They need to be very attracted to water for them to be able to absorb large amounts of water. And they're by definition capable of swelling by absorbing large amounts of fluids. Okay. So the next option is they have predictable or known swelling rates. Is this true? Can we predict the amount of swelling a hydrogel will undergo? Is it possible for us to predict? We can, right? So for a given mass of hydrogel, if the amount of water, so the volume of water is so and so, or the amount of fluid that's present in its environment is so and so, we can calculate or predict the amount of swelling the hydrogel will undergo through. So that's not an issue. So it's correct. And are they insoluble due to physical and chemical crosslinks, which provide the network structure and physical integrity? Or are they soluble in water? So are hydrogels insoluble or soluble in water? Both of them cannot be true. So one of them has to be wrong. So hydrogels are hydrophilic, meaning they attract a lot of water. But are they insoluble in water or soluble in water? Any idea?
So soluble in
Uh,
water.
Sir, I think they are soluble in water.
Okay. Okay. So generally hydrogels are insoluble in water, especially because of so if it's a chemical crosslink, it's a covalent bond, right? So water cannot simply go and break a covalent bond, and same holds true for most ionic bonds. So if you want, you can make a soluble hydrogel, but in general, hydrogels are not soluble in water. So they are insoluble in water. Simply because of the fact that so you want them to swell, right? So let's say you're taking this hydrogel and putting it in a container of water. You would expect this to become something like this. So if it's soluble in water, it will become something like this, right? So it will slowly start to get solubilized in water. It will not increase in its mass. So it will readily be solubilized in water. So yeah, so they're not soluble in water. So this is wrong statement. And do they have low burst effects? So burst effect is previously we've talked about if a polymer, a controlled release system is loaded with drug. If it's kept for a long time, if it's an old controlled release device, the drug diffuses to the surface of the device. And when it's put in a biological medium, serum, what happens is the drug that's at the edge of the device starts to diffuse out. So is this problem lower in hydrogels or higher in hydrogels or not changing in hydrogels? No reason for it to be low, right? So because you would still, so even if the hydrogel has drug, you would want the drug to diffuse out of the hydrogel, especially once it has swollen. So the pore size here is very small. So the drug might not readily diffuse, but the pore size here is quite big. So the drug is able to readily come out. But even though the pore size is small, a little amount of drug will, if it's kept for a very long time, there's bound to be drug that's going to reach the boundary of the hydrogel, and as soon as the hydrogel swells, it will immediately release the drug. So they have low burst effects is not true, right? Right?
Yes, sir.
Any other thoughts?
Can you explain once again, please?
Yeah, so my argument is hydrogels still have pores, so drug is bound to come out of these pores and get concentrated on the surface of the hydrogel. So when the hydrogel is put in water or any fluid, even though these pores are becoming bigger, there is drug that's already at the boundary because it diffuses out of these pores and it will release these drugs very immediately. So you see a burst effect. So this might be happening, but compare that to what would happen in other control device systems. So here we do not, so even though we know the pore size is more or less remaining constant. It's not increasing, meaning the pore size must be big enough for the drug to able to freely diffuse out, right? So you want to ensure that whatever drug is present here is able to diffuse out of these pores, but for a hydrogel, that's need not necessarily that's not true, right? So you can in fact decrease the pore size so much that such a few amount of drug is going to diffuse through them, and only good amount of drug is going to diffuse when it's put in water and it's fallen. So the amount of drug that reaches the periphery is much lower compared to what would happen in other controls release systems, right? So it would observe low burst effects. You would observe low burst effects in a hydrogel compared to other controlled release systems. You will still have burst effects, but the amount of burst that you see is much lower in hydrogels compared to other controlled delivery systems. Is that clear? You guys have any questions?
Sir, last two statements, how?
Yeah, so essentially what I'm saying is, so if you have a controlled release system, let's say it's not a hydrogel, it's some polymer controlled release system, right? So you are loading your drug in and you want the drug to come out. So because it's not a hydrogel, this will also have pores in it. And so the drug will diffuse freely through these pores, right? Because it's not a hydrogel, these pore sizes are not going to increase at any point. You don't have any reason to think that these pore sizes would increase. So these pore sizes, you want to ensure that the drug is able to diffuse out at some constant pace. So so because you're designing these pores in such a way that the drug is able to diffuse out at a constant pace, what will happen is if you keep this device for a very long time, that a lot of drug is going to get saturated at the periphery of the device because it's already, so the center of the device is where the drug concentration is the highest. But it has been kept for a long time, so natural diffusion would occur, and a lot of drug is going to get deposited in the periphery of the device. So when you put this in water, you see this burst release of drug, where this is the graph, right? So something like this. Even initially, there's a very large amount of drug that's getting released. So same thing can happen in hydrogels, but the good thing, the advantage of hydrogels is you don't have to design these pores initially, these pores in such a way that the drug is able to diffuse. You can design very small pores. The drug is not able to diffuse out of them. So very little amount of drug is going to reach the periphery. But these pore sizes are going to increase when you put it in water, right? So when you put it in water, the hydrogel is going to swell, it's going to expand, and these pore sizes will increase. Then the drug can come out. So the amount of burst that you see in hydrogels would be something like this. So it's going to be very less compared to what you would observe in a normal control release system. So they have low burst effects. Clear? Hello? Okay, so if you have questions, stop me. But yeah, so the next point is they're used in contact lens. Is this true? It is in fact true. Hydrogels are very useful for contact lens manufacturing, especially because of the fact that they can retain a lot of water, right? So they can continuously moisture your cornea and not let it dry up. So they're very useful for contact lenses. And are they suitable for all routes of delivery? Are hydrogels suited for all delivery routes? Let's think of examples, right? So let's say a patient is suffering from asthma and you want to deliver a drug to his lungs through inhaler. Can you deliver hydrogels through inhalers?
No.
Yeah, so they're not, or if you want to deliver to the brain, or so many different cases where hydrogels are not very suitable. So they are insoluble in water and they're not suitable for all routes of delivery. So those are the correct answers. Okay. Okay, so moving on, what is the heat capacity of a system? Is it the heat required to increase the temperature of surface by 1 Kelvin, system by 1 Fahrenheit, system by 1 degree centigrade, or surface by 1 degree centigrade? What do you guys think? What is the heat capacity of a system? Is it so a couple of things going on here, right? So either surface increase or system increase, either by Kelvin, Fahrenheit, or Celsius. So do you guys think heat capacity of a system is surface increase of temperature or system increase of temperature? So the name itself implies, right? So it's heat capacity of a system. So is it surface increase or system increase?
System.
Correct. So it's not the surface increase of temperature, it's the system-wide increase of the temperature. Now, is it increased by 1 degree Fahrenheit or 1 degree Celsius?
For Celsius,
Yeah, correct. So Fahrenheit is not generally used for scientific definitions, so you can ignore that. So heat capacity is heat required to increase the temperature of a system by 1 degree Celsius is correct. Now, if I were to say, no, it is the heat required to increase the temperature of, instead of surface, I'll say system by 1 Kelvin. Would that be true? So, can I define heat capacity of a system as heat required to increase temperature of a system by 1 Kelvin?
No.
Okay. You can. So the the difference of temperatures in Kelvin and centigrade are the same. So it's not a problem if you define it using Kelvin as well. So, but in this case, it's wrong because they're saying the surface by 1 Kelvin, which is wrong. If it's system by 1 Kelvin or 1 centigrade, then that's fine. But usually it's defined as heat required to increase the temperature of a system by 1 degree centigrade or Celsius. Okay. Okay, so moving on. The next question is, when the drug loaded is greater than its solubility, which of the following is true for drug release from scaffolds? The interface between dissolved drug region and dispersed drug region moves into the interior as a front. The interface between dissolved drug region and dispersed drug region moves into the exterior as a front. Or the interface remains stationary, or will the system not behave dynamically, meaning it's static, it's not going to change over time. So I'll repeat the question once again. So when the drug loaded is much greater than its solubility, what will happen to drug release from scaffolds? First of all, will the system not behave dynamically? Will the system remain stationary and static throughout time, meaning no drug is released? No, right? Drug will eventually get released. So the system will not be static, it will behave dynamically. So it will change over time. Now, how will it change over time? Does the interface between the dissolved drug region and dispersed drug region move to the interior as a front, or does it move exterior as a front, or does it remain stationary? If it remains stationary, again, it means that the system is more or less stable, right? So no drug is being released. So obviously that's not true. So the only two key choices that we have are does the interface move into the into the interior or into the exterior? Any idea? What are they talking about here? What is this interface?
The interface is nothing but boundary, sir,
Yeah, between the dissolved drug region and the
uh,
dispersed drug
and
region.
dispersed drug region.
Correct. So, what is dispersed drug region?
So it may be exterior as front.
Okay, so let's first try to understand what's happening here. So, there are two terms here. One is dispersed drug region, and the other one is dissolved drug region. Right? So what is a dispersed drug region? So remember, the drug loaded is greater than its solubility. So the dissolved drug region is going to be, at least initially, low compared to the dispersed drug region. So what is a dispersed drug region? So dispersed drug region is simply, so let's say you have this system. Uh, there's a lot of drug here. Now the solubility of this drug is low, right? So, and there's no water in the system. So all of this drug is dispersed. So this is the dispersed drug region. And if you put this in a biological system, so there is serum or water that's present all around, right? Now slowly this water will start to get into the system because it's a scaffold, and slowly the drug will get dissolved. At least the drug that's on the periphery will start to get dissolved. So this is the dissolved drug region. So they're saying the interface between the dissolved drug region, which is this, which is on the outside of the or the periphery or the boundary of the system, and the dispersed drug region, which is the core. Now, so the interface between them is this. So they're asking over a time period. So as the time progresses, how is this interface going to change? Does it move inside, meaning more water is entering the system, or does it move outside, meaning water is leaving the system and the drug is not getting dissolved at all? What do you guys think might happen? So if it's moving into the system, the dissolved drug region is increasing over time, right? So this is slowly shifting up into the core of the system. So the dissolved drug region is increasing, meaning more and more drug is getting dissolved as time progresses, and water is infiltrating the system. But if it's moving outside, less and less drug is dissolving over a period of time, meaning water is going out. So the drug is going to stay in the scaffold itself. It's not going to go out anywhere because it's not getting dissolved and being taken away by the water. So, what is true for drug release from scaffolds? What do you think is happening over a period of time? I will draw one more. Maybe this is not clear. So let's say I have a bar. So this is my drug delivery system, right? Now I have a lot of drug in the bar. I have a lot of drug. Okay. So all of this drug is not dissolved. So it's not dissolved drug, it's just dispersed in the system. So this is the dispersed drug region. This entire thing is dispersed drug region. Now, if I put the system in a biological media, what would happen? Water will slowly start to creep in. So let's say this is where the interface for the biological media is. So water will slowly start to get inside. And once water gets inside, what will happen is so this entire thing is of drug. So whatever drug is here will slowly start to get dissolved. So this is dissolved drug region. This is dispersed drug region. This is dissolved drug region. Now this is the interface between both of them, or the boundary between both of them. Over a period of time, what will happen? So if I am to look at it at 0 hours, 1 hour, 2 hour, 3 hour. Do you guys think more and more water will get in and slowly this region will shift and start moving into the interior of the device? Or do you guys think it's going to stay there itself? Or do you guys think somehow it's going to be pushed outside and slowly move to the exterior of the device?
Sir, interior.
Right? So because more and more water is getting in over a period of time, the interface will slowly start to move towards the interior of the device, right? So uh, I don't know if you guys have gone through these, but yeah. So essentially, what's happening is this entire region is dispersed drug, but since water is slowly getting in, the dissolved drug region is increasing slowly over a period of time, and this will slowly start to move to the core of the system and increase over time. So yeah, the interface between dissolved drug region and dispersed drug region moves into the interior as a front, not exterior. Is that clear? Any questions? Okay. Okay. So the type of hydrogels that polymerize after injecting into the body are called what? Physical cross-linking hydrogels, chemical cross-linking hydrogels, in situ cross-linking hydrogels, neutral hydrogels, photo-linked hydrogels, or enzyme-linked hydrogels. What do you guys think? So these hydrogels are polymerizing after injecting into the body, not before. So before they might exist as individual components, but this mixture will only start to polymerize once it's entered the body. So what are such hydrogels called? Are they physical cross-linking hydrogels, chemical cross-linking hydrogels, in situ cross-linking hydrogels, neutral hydrogels, photo-linked hydrogels, or enzyme-linked hydrogels?
Sir, is it in situ cross-linking hydrogen?
Yeah, correct. So they're called in situ cross-linking hydrogels. In situ meaning in the body. So in the body cross-linking hydrogels, which are hydrogels that cross-link inside your body. So the polymerization triggers can be several things: time, temperature, pH, light, magnets, whatever it is. So those are in situ cross-linking hydrogels. Okay. Okay, so moving on. What is true for bioerodible matrix delivery systems? Pick two correct statements. Are they degradable, more patient compliant? Are they non-degradable? Are the byproducts of degradation always highly toxic? Or can they achieve first order with surface eroding polymer devices? What is true for bioerodible matrix delivery systems? Are they degradable or non-degradable?
They are degradable.
Right. So bioerodible, right? So they are
Yeah,
degradable. Okay. Uh, so are the byproducts always highly toxic?
but in this question, it doesn't. It should be less. I mean, it should not be toxic.
Correct. So if the byproducts were always highly toxic, then they will never be used for drug delivery, right? So
Yeah.
yeah, so they are not highly toxic. Often, in most cases, they're very simple molecules that your body can break down. And can they achieve first order with surface eroding polymer devices? They can. You can achieve for first order release kinetics with surface eroding polymer devices. So that's also true. So they're degradable, more patient compliant, and can achieve first order kinetics with surface eroding polymer devices. Okay. Moving on. So this is a numerical, I guess. In a membrane reservoir system with 5 microns membrane thickness, 5 mg of drug is released after time t. If the desired release of drug is 1 mg, what should be the thickness of the permeable membrane? Report your answers in micrometers. So essentially what they're asking is, you have a membrane reservoir. It has 5 micron membrane thickness. 5 mg of drug is released from it after time t. But you only want 1 mg of the drug to be released in that time t. So then what should be the membrane thickness instead of 5 microns? Do we know how to solve this?
So, is there, because in the first part of the question it's mentioned after time t. So, in the second part, is there any particular time?
Yeah, so it implies that you're looking at the same time t. So you only want 1 mg of the drug to be released in the same time t, whatever the time t is.
So it should be 1 micron.
How?
So if we are going through the formula mt is equal to 80k CST by L, so
Right?
so if we are dividing both of them, then for 5 microns, if it is 5 mg of drug, then for 1 mg of drug, I think the thickness should be 1 micron.
Right. Correct. So everyone remembers this formula. So for a membrane reservoir system, uh, the amount of drug released at time t is given by the surface area of the release times the drug diffusion coefficient through the polymer carrier times the partition coefficient times the drug solubility in the polymer carrier divided by the thickness of the rate controlling membrane, and t is the duration of release, right? So here L is initially 5 microns, and over a time period of T, they're saying 5 mg of the drug is released. Now, what they're essentially asking you to calculate is what should L be if this is changed from 5 microns to 5 mg to 1 mg for the same time T, right? Okay. So with that formula, what you can do is now, so 5 mg of drug is released. You have 80K CST. So you don't know these values, but you do know the length, which is 5 micron, right? So which implies this entire thing combined together is around 25, or whatever the units might be. Now, for 1 mg, they're asking what should be the length. So, you know, this is not changing. So, either the surface area of the release, the drug diffusion coefficient, the partition coefficient, the solubility of the drug in the polymer, or the time, none of them are changing. So, this remains constant at 25, which you have calculated previously. All you have to do is calculate the length. So essentially what you'll do is for 1 mg is equal to 25 by L, or L would be 25 micrometers is what you would get. Is that clear? How did you get 1?
I think I did a miscalculation.
Okay, so is it clear now?
Yeah.
Yeah, so you have initially you have this and this, and what you want to do is since this is remaining constant, you want to find out what the value of that is, and the next time you don't have this, but you have this, so you know this from previous calculation, so you just substitute and get the answer. Fairly straightforward. Okay. I think that's all for week 3's assignments from last year. So do you guys have any questions? Do you guys have any other questions in any of the week 3 syllabus? If not, that's fine. So you guys also have 2 more sessions on Monday and Tuesday, right?
Yes, sir. Yes, sir.
Yeah, so where they will also be discussing this problem. So do you guys want me to do something different? Do you guys want me to go through the course a little bit or just go through the questions themselves? Which do you guys think is going to be more helpful? Okay, I guess in that case, I'll just go through the questions themselves and see if anything comes up and we can discuss them. Sounds fair?
So you can go through some.
If we are having any doubt about a particular topic, we can also discuss about that in these sessions, right?
Yeah, yeah, you can.
Okay.
Yeah.
Okay.
So if you have any doubts or if some concept is not clear, please feel free to bring it up.
Yeah.
We'll go through it, we'll discuss it, and we'll try to understand it better.
Okay.
Yeah. Okay, okay then. See you guys on next Saturday, I guess. Thank you for joining in. Take care. Have a good weekend. Bye.